now that we've learned quantitatively about this whole idea of leading clock's lag, let's return to our star tours example, our trip to a star 5 light years away. So let's remind ourselves what was going on there. So I've added a few things to the original diagram, but essentially Earth, Alice on Earth, star 5 light years away, according to Alice's lattice system of measurement and clocks. Bob traveling along at velocity v, and we're going to say v is 0.943 c, mainly so that we can say gamma is 3. And we did it from Alice's perspective, the Earth observer perspective. We said, okay, 5 light year distance. We see Bob traveling along at 0.943 c. The time it takes him then will be 5.3 years. In other words, and I've drawn in here, this is the Earth star system lattice of clocks there, the imaginary lattice of clocks. And so when Bob passes by, remember when Bob passes by Earth on his trip here, Bob's clock will read 0. Alice's clock on the Earth system will read 0 right at that point. So they both are measuring time from that instant on their clocks. They just set their clocks so there's 0 at that point. So then as far as Alice is concerned, Bob moves along. When he gets to the star, another photograph is taken to compare the two clocks at that time. And Alice on her clock, in the star system clock, Earth star system, will read 5.3 years. Because it's 5 light years, 0.943 c, takes 5.3 years to get there. But then when she looks at the photograph of Bob's clock as well, what does she read? Well, to her, Bob is traveling along at speed v. There's a time dilation effect. She sees Bob's moving clock running slow. And for a gamma factor of 3, what that means is that her clocks tick off 5.3 years. His clock, from her perspective, as she's watching the moving clock go by, ticks off 5.3 divided by gamma, which is 3, 5.3 divided by 3, 1.77 years. So that's the photograph. In that photograph there that's taken, that's what Bob's clock says, 1.77 years. Now, Bob can't disagree with that. He says, yeah, obviously, it's 1.77 years. I see it. It's in the photograph. I looked when I went by, too. It's 1.77 years. And Alice's result is 5.3 years, and that's the part you may remember was at that when we first did this, we really didn't have the capability to understand that, and that's what we're going to do now in a few minutes. But let's continue on here. What's Bob's perspective? He's the rocket observer. He observes, in his frame of reference, the Earth star system moving to the left, and therefore he sees the star rushing toward him at 0.943 c. And therefore this 5 light year distance, 5 light years to Alice, to him is only 1.67 years. It's a contracted distance. The distance for the Earth star system, from Bob's perspective, the rocket perspective, is 5 light years divided by gamma, gamma being 3, and that's 1.67 light years. So to Bob, he sees, when he just passes Earth, he sees the star 1.67 light years away and traveling toward him at 0.943 c. Therefore, the time for the star to actually reach Bob and then have the photograph taken is 1.67 light years, the distance, divided by 0.943 c. We're taking c to be 1 light year per year. And therefore, it comes out to be 1.77 years. And he says, yes, absolutely. That's what my clock should say. That's what the photograph shows. And I agree absolutely, because I traveled for 1.77 years. The distance was 1.67 light years. The speed, actually I should back up, he didn't travel for 1.77 years. The star traveled toward him for 1.77 years. Is a distance of 1.67 light years, the speed 0.943 c. It all works out to him. But then we asked the question, and well, we held off on this. We said, how does Bob explain this 5.3 years business, especially when we took the next step and said, okay, shouldn't time dilation also apply to Bob observing Alice's clocks? It applies for Alice observing Bob's clock here, or system of clocks. Bob, of course, has his own lattice of clocks, which we didn't draw in here. But doesn't it apply the other way as well? And the answer is absolutely it does. So we said Bob's observation of the lapse time on Alice's clock. So he's sitting there, he's watching Alice's clocks go by. He compares the timekeeping on her clocks to his clock and sees a time dilation factor such that, I squeeze it in down here, it's 1.77 years. That's the elapsed time he sees on his clock as the star rushes towards him, and divided by the gamma factor. So he sees the elapsed time on Alice's clocks from when Earth was next to him to when the star goes by as 0.59 years. And that's the big puzzle then, or was the big puzzle, because we say 0.59 years, that's what Bob sees Alice's elapsed time being. Alice is seeing 5.3 years. In fact, the photographic evidence shows that when, say, this clock right here, okay, so here's here's that clock that's going to get photographed when it gets over here to Bob. When that clock reaches there, the photographic evidence shows that it's reading 5.3 years. And yet Bob's saying it should only be 0.59 years. Well, as I mentioned when we first did this, this is a very nice example because it shows that in these types of problems, typically you have to think about time dilation. It comes into play. You often have to also think about length contraction. It comes into play. And often people just think about those things and they forget one of the key things about the special theory of relativity that comes into play in these problems. A third thing that comes into play, and that's a relativity of simultaneity. And this is where you get into trouble, where you get these weird paradoxes sometimes that don't seem to make sense. And you say, well, gee, maybe the special theory of relativity is wrong. After all, it's really, you have to remember the relativity of simultaneity. And that the relativity of simultaneity, one aspect of that is the fact that leading clocks lag, as we showed qualitatively a while back. And now quantitatively, we know that the factor by which they lag by is dv over c squared, where d here is, so this is where you're in a frame of reference and you're observing clocks going by you with some velocity v. Okay, so they're in a separate frame of reference, they're moving by you. So in this case, Bob is in his frame of reference, sitting in his ship. He's observing Alice's clocks move by him. And pick any two clocks in that lattice, and the distance between them here is the distance in the moving frame of reference. Okay, so it's the distance that Alice sees between the two clocks, not the distance Bob sees between the two clocks. That's important because Bob's distance is contracted, as we saw, but it's the distance between that Alice sees in the clock's frame of reference. Okay? V is the velocity of the two frames of reference, and of course, c squared here. So let's apply it to our situation here. Okay? So photograph is taken right here. Clocks, both Bob's clock and Alice's clock, read 0. The star, from Bob's perspective, travels to him. Another photograph is taken at that point, or from Alice's perspective, Bob travels to the star, photograph taken. And again, we said to Bob's perspective, the elapsed time while he waits for the star to get to him between the 0 time here and the star gets to him is 0.59 years. Okay? And yet clearly the clock, this clock, the photographic evidence shows it reads 5.3 years. How do we understand that? Well, it's the leading clock's lag factor. It's the relativity of simultaneity. Because at the beginning here, okay, right when Bob is next to Earth, the star is moving toward him, these clocks, they both read 0. Well, at that point, for Bob, if he had his whole lattice of clocks here and took photographs, so Bob has his own, lattice of clocks. Let's find my green pen here. So Bob, I guess we'll make that green there, but Bob, has his own lattice of clocks, imaginary, of course, but useful for making measurements. And so at that instant in time, when this photograph is taken, if he wanted to, he could take photographs all along his synchronized lattice of clocks. And in particular, he could find out what that clock is reading at that instant in time. And so let's think about this. Leading clocks lag. Bob is seeing this whole sequence of Alice's clocks move by him. This clock here, we know at that instant in time is t equals 0. It's reading 0. What does this clock read according to Bob, according to his synchronized lattice of clocks? Well, that clock is the clock in the rear. This clock here, and note that here's the distance d, make this clear here. That's the distance d that Alice sees between those two clocks, her distance d. That's this distance. Bob sees a lag between that clock and the clock at the star here that's eventually going to get to him. That lag is going to be dv over c squared. In other words, if this is 0, leading clock's lag, so this clock, as it's moving this way, lags this clock. This clock is ahead. Clocks in the rear are running ahead of clocks in the front. Leading, or the way we've been saying, leading clocks lag. The clocks in front lag behind a clock in the rear if you have clocks moving past you. And so this clock right here lags behind this clock by this factor. Well, let's put some numbers in now. So d is 5 light years. V is 0.943c. C squared, we're using light years, so c squared, c is just 1 light year per year squared, just 1 squared. Do the math on what you get here. You get 5 times 0.943. You get this right? 4.71. Again, I just semi-memorized that. 4.71 years. Let's make sure we understand that. In other words, at the instant when Earth and Bob are lined up here, and both the clocks here read 0, from Bob's frame of reference, if he took a photograph of the star clock out there that is moving toward him, it would read 4.71 years. Alice's clock here reads 0. This clock, and it lags this clock here by 4.71 years, which is based on the distance between the two clocks in Alice's frame of reference and the relative velocity between them. If you took a clock halfway along the way, if Bob looked at this clock, then 4.71 years would be what, about 2.36, something like that, 2.355, whatever, years distance. So all these clocks, the farther away you get here, the more the lag time, or the more really these clocks are ahead of the leading clock, and we're designating this as the leading clock. Okay? But you say, well, wait a minute though. We're trying to get 5.3 years on this clock. When this clock reaches here, the photograph evidence shows it reads 5.3 years. That's not 4.71 years is not 5.3 years. But remember, the elapsed time between this instant, when Earth is here, and then when the star gets there, is 0.59 years, according to Bob's clocks. So, I should say not according to Bob's clocks. That's the elapsed time he sees on Alice's clocks. Okay, they're running slow compared to him. So as they're going by, he's watching them tick off, and he sees them tick off 0.59 years. And it reaches here, but this clock started 4.71 years ahead. And so 4.71 plus 0.59 years, 4.71 plus 0.59, 5.3. And it all hangs together. It's all consistent. As long as you remember to put everything in there in terms of the special theory of relativity. We've got time dilation involved in this. Both ways, to Bob and Alice, we've got length contraction as well. The way we were analyzing it is really Bob viewing the length contraction there, but you can reverse things and also do Alice's perspective and length contraction for for Bob. If Bob had two spaceships here, one here and one here, then Alice would see a length contraction for Bob's distance between them, and so on and so forth. But the point here is that when this clock reaches here and the photographs are taken, this clock says 5.3 years. Alice understands that very easily. Just 5 light years divided by 0.943c. Sure, it's got to be 5. Of course, it's 5.3 years. My clocks are all synchronized. It started out at 0. Took 5.3 years. Yes, it's going to read that. And Bob's clock reads 1.77 years. And again, Alice understands that. She says, yes, because your clocks are running slow, Bob. So they only ticked off 1.77 years. And meanwhile, Bob says, well, my clock's just fine, but the fact that it's 1.77 years is because I didn't have to travel as far. It's your distance that's messed up, Alice. It's not 5 years. It's 1.67 light years. Okay? So I traveled according to my clock, I didn't travel. The star traveled toward me For 1.77 years, there's a distance of 1.67 light years at 0.943 c. It all makes sense to me. And then the final thing that Bob has to explain to make sense is, how does Alice read this 5.3 years on the star clock when it reaches Bob? And they take the photograph. And the answer is, from Bob's perspective again, that he sees Alice's clocks time dilated, that if his clocks tick off 1.77 years, he sees her clocks tick off 0.59 years. But this clock back here at the star, when it starts off here and Earth is right next to Bob, is already 4.71 years ahead because of the leading clock's lag factor, the relativity of simultaneity. So that it's reading 4.71 years right here, according to Bob's perspective, and then Bob watches it tick off as it gets closer and closer, and when it reaches here, it is ticked off an additional 0.59 years. 0.59 years plus the starting value of 4.71 years gives us the 5.3 years, and Bob says, yes, of course your clock says 5.3 years. Not because you're right, your clocks are all messed up, they're all unsynchronized, but yes, we can agree that that's what should show 5.3 years, and they both agree that yes, the 1.77 years should show on Bob's clock, but for different reasons there. So again, something to ponder here, to sort of work through in terms of how time dilation works into it, how length contraction works into it, and then sort of the missing factor that's people often forget about is the relativity of simultaneity, that you get this desynchronization in a sense that Bob's clocks are synchronized to him, Alice's clocks are synchronized to her in her Earth star system, but when one looks at the other's clocks, they are not synchronized. And the leading clock's lag factor is this dv over c squared. D being the distance in the moving frame you're thinking about, times the velocity divided by c squared.